Hello everyone, welcome to our channel Off Campus. In this video, we are going to discuss about some multiple choice questions in semiconductor physics. First, we start the video. First question: in an intrinsic semiconductor, the Fermi level lies at the center of forbidden energy gap, is near the conduction band, is near the valency band, may be anywhere in the forbidden energy gap. What is the question? In an intrinsic semiconductor, the Fermi level lies at the center of the forbidden energy gap. Option A is the right answer for this problem question. Then question number 2, the ratio of impurity atoms to intrinsic semiconductor atoms in an extrinsic semiconductor is about. Option D, 1 is to 10 power 8. This is the ratio of the impurity atoms to intrinsic semiconductor atoms. Okay. Then in a p-type material, the Fermi level is 0.3 electron volt above the valency band. The concentration of acceptor atoms is increased. The new position of Fermi level is likely to be 4 different options are given. What is given in the question? The concentration of acceptor atoms is increased. Whenever the concentration of the acceptor atom is increased, the Fermi level will be closer to the valency band. It will be the closer to the valency band, which means that 0.2 electron volt above the valency band. Okay. So, option B, 0.2 electron volt above the valency band is the right option for this question. Then question number 4, most commonly used semiconductor material is, the answer is option A, silicon. Silicon is the most commonly used semiconductor material. Then question number 5, at room temperature a semiconductor material is slightly conducting. At room temperature the semiconductor material is slightly conducting. Option C, slightly conducting is the right option. Then question number 6, for silicon the energy gap at 300 Kelvin is, option C, 1.1 electron volt. Option C, 1.1 electron volt. Then 7, the forbidden gap for germanium is 0.72 electron volt. Option B, 0.72 electron volt. Okay. Then the process of adding impurities to a semiconductor is called, what is the name called? The process of adding impurities to a semiconductor is called mixing, doping, diffusing, none of the above. The process of adding impurities to a pure semiconductor is called doping. Option B, doping is the right option. Then question number 7, the pentavalent impurities. What are all the pentavalent impurities? Like antimony, arsenic, bismuth and phosphorus added to intrinsic semiconductors are called. 4 different options are given. Whenever the pentavalent impurities are added, it is called donor impurities or donor atoms, or n-type impurities. Donor or n-type. Option D, donor or n-type impurities is the right option. Then question number 10, impurities like boron, aluminum, gallium, indium are added to intrinsic semiconductor to form p-type doped semiconductor. Whenever impurities like it is also called as acceptor impurities, p-type or acceptor. Otherwise, what is that? Impurities with which impurities is known as, these impurities are called as trivalent impurities, whereas for donor and n-type impurities, pentavalent impurities, it is called as, for p-type, or it can be called as acceptor. Okay, acceptor impurities. Which impurities can be added? Borons, aluminum, gallium or indium are called as trivalent impurities. For trivalent, it is p-type or acceptor semiconductor, whereas in pentavalent impurities, it is whenever the pentavalent impurities added to the intrinsic semiconductor, it is called as donor or n-type impurities. What are all the pentavalent? Antimony, arsenic, bismuth and phosphorus. What are all the trivalent impurities? Boron, aluminum, gallium or indium. These are all very important. Okay. Then move on to the next one. In n-type semiconductor, the position of Fermi level. What will be the position of Fermi level for n-type semiconductor? It is higher than the center of energy gap. Option C, higher than the center of energy gap. Then this one, question number 10, the mobility of electrons in a material is expressed in a unit of, what is the unit of mobility of electrons? What is the formula? How can we find out the formula for mobility? How can we find velocity? V equal to mu e. Mu is denoted as mobility, where velocity is velocity of the material, velocity of that electrons, V, whereas V equal to mu e. E is electric field. What is mu? Mobility equal to V by E. What is the unit of V? Velocity, meter per second. So what is the unit of denominator? In denominator electric field. Now electric field, what is the unit of electric field? Already we can V by D, nothing but voltage per E equal to V by D. So it is E equal to V by D. In denominator, in numerator, mu equal to velocity by electric field E. Okay. In numerator, what term is there? Velocity. What is the unit for velocity? In numerator, velocity unit is meter per second. When then coming to the denominator, what is in the denominator? Denominator is nothing but in denominator there is electric field. So what is the formula for electric field? E equal to V by D. So V equal to voltage, D is a distance. In denominator, what is the unit? Voltage per second. Numerator, meter per second. In denominator, voltage per second. So by solving, what we will get? Meter square per voltage second. So voltage per second, okay, meter square per voltage second. Option B, mobility of electron in a material is expressed in unit of meter square per voltage into second. Okay. Then in a metal, the electrical conduction is by electrons and holes. The conductivity decreases with rise in temperature. The conduction band is empty, none of the above. In a metal, the conductivity decreases with rising temperature. Option B. Then question number 14, the energy gap in a semiconductor increases with temperature, does not change with temperature, decreases with temperature, is 0. So which one? In the energy gap in a semiconductor decreases with temperature. Okay. Then it is on problem. Two initially identical samples A and B of pure germanium are doped with donor concentrations of germanium. Donor concentration is nothing but electron concentration. For sample A, what is that? 1 into 10 power 20. For sample B, what is the electron? Donor concentration is otherwise known as electron concentration. For sample A, this value, and sample B 3 into 10 power 20 respectively. Then if the whole concentration in A is 9 into 10 power 12, then the whole concentration in B at the same temperature will be. So what is given? 2 samples of pure germanium. Okay, identical samples are given. Donor concentration, which means that electron concentration is given for sample A and B, and whole concentration is given for sample A only. So we need to find out the whole concentration for sample B. We will see how to find out. For sample A, what is I have written one by one here. For sample A, what is given? Electron concentration value 1 into 10 power 20. For sample B, what is the donor, or otherwise called as which one? See, donor concentration, or otherwise called as electron concentration. For sample B, 3 into 10 power 20. For sample A, whole concentration is given. We need to find out the whole concentration for sample B. So we know the Morse action law. What is the Morse action law for n type? See, Ne, electron concentration, into whole concentration is equal to intrinsic carrier concentration Ni squared. Nn equal to Ni square, or majority carrier concentration and minority carrier concentration equal to intrinsic carrier concentration. Majority into minority carrier concentration equal to intrinsic carrier concentration. So what is the majority concentration for sample A? So for sample A, 1 into 10 power 20. What is the minority carriers here? Majority is electron, minority is hole concentration. Hole concentration equal to, for sample A only we are checking, okay, into 9 into 10 power 12, majority into minority for sample A, okay. Then what we will get, 9 into 10 power, just add the power, 9 to 1 we will get 9 only, adding the powers 20 plus 12, 10 power 32, which is equal to the intrinsic carrier concentration Ni squared. So we know that Ni squared. How can we find the whole concentration? We know the Ni squared value here, intrinsic carrier concentration. So we know the which one? Sorry, sample B. We know the sample B. For sample B, electron concentration and intrinsic carrier concentration we know. What is the minority carrier concentration here? So Nn equal to Ni squared by Ne. Sorry, Ne it is, okay. Okay. This is, we know the sample B, right, electron concentration value, and we need to find out the whole concentration, because electron into whole concentration, majority or otherwise majority and minority concentration equal to intrinsic carrier concentration. So this one Nn, this is sorry, for sample B electron concentration is Ne, okay, Ne into Nn equal to Ni squared. So what is Nn? We need to find out the whole concentration. Nn equal to Ni squared divided by Ne. We know that value of Ni square, 9 into 10 power 20. What is electron concentration for sample B? Divided by 3 into 10 power 20. So 9 by 3, nothing but 3. 32 minus 20, what will get? 12 meter power minus 3, okay. This is the whole concentration value for sample B. See, option A, 3 into 10 power 12 meter power minus 3 is the right answer for this problem. Okay, thanks for watching. Please like, share and subscribe our channel Off Campus, and kindly check with the playlist. If you haven't seen those playlists still, kindly watch those playlists, and we have discussed many topics under engineering and electronics and communication engineering. We have discussed engineering mathematics problems and in different topics, and microprocessors, signals and systems, in various ECE subjects we have solved and discussed and short notes of that all subjects. So kindly check with the playlist and subscribe our channel, share, like, and thanks for watching.